the pH, something called the POH, the hydrogen ion concentration, and the hydroxide ion concentration. So this would fully characterize a solution of let's go with 200 molar ammonia, NH3, as an aqueous solution. We need a balanced reaction. Ammonia, NH3, is a weak base. A weak base will accept a proton right here. Nitrogen's got a lone pair of electrons suitable to do this. And we're going to put it in water. We definitely have equilibrium. I said definitely because this is recognized as being a weak base. And this is going to give an H4 plus and hydroxide. Well, equilibrium time. We have 0.2 molar, 0.200. It's not going to stay there. We're going to lose a little bit because it's a reactant, so I'll put minus x. All the stoichiometry is 1 to 1, so we're going to make plus x of this and plus x of this. Before class, I looked up the equilibrium constant for this. The products over reactants constant is listed as Kb. The little b is for base because we're doing a base reaction. And one source I found says that it's equal to 1.78 times 10 to the negative fifth, which is equal to x squared over 0.2 minus x. Again, let's lose that x, so we have no need to solve for the quadratic formula. And we can solve by cross multiplication and taking the square root. Now, in this case, x is not going to be proton concentration. We're doing a base. It's going to be hydroxide ion concentration. So x is going to give us the hydroxide ion concentration. So after cross multiplication, I have x as being equal to 0.0019. Well, in order to get to the pH, one of the shortest routes is to calculate the POH. The formula for that, the POH is equal to the negative log of hydroxide ion. So like we have the pH, power of hydrogen, we have the power of hydroxide. So plug this in, negative log of 0.0019, and we calculate the POH to be 2.72. The relationship between the POH, which was one of the items we wanted to find here, is 14 is equal to the sum of pH plus POH. The pH plus the POH sum to 14. So just by subtraction, 14 minus 2.72 gives us the pH of, I'll call it 11.3. I'll go to 3 sig figs here. This is just wonderful. Now, we have 3 out of the 4 in our wish list. We have the hydroxide ion concentration, we have the POH, we have the pH. The way to get to the proton concentration would be something like this. The pH is equal to minus the log of H plus. Well, in this case, we know what the pH is, and we can solve for this. Change the sign on both sides, so in other words, multiply by negative 1, and take the anti-log. Gives us a nice, simple little formula. It says the hydrogen ion concentration is equal to 10 to the minus pH. Mathematically, 10 to the x is the anti-log. So if we change the sign, as I mentioned before, this becomes negative, and then we take the anti-log, we get this. So on our calculators, to calculate our very last quantity we'd like to know, proton concentration, on our calculators we're going to hit the 10 to the x button to the minus pH. So this is going to be 10 to the minus 11.3. Let's see here. I calculate that to be 5.3 times 10 to the negative 12. A very low concentration of proton, which makes sense because we have a basic solution.